Hello, everyone. My name is Osvaldo Angtuncio, and I'm going to talk about the profile of trees with a given degree sequence. This is a joint work with Jerónimo Uribe Bravo. First of all, we will work with rooted finite plane trees, meaning that in our trees, we keep track on the way in which vertices are born. And we are going to label them in breadth first order, meaning that the root, which is at generation 0, has label 1. Then its children, which are at generation 1, are labeled from left to right, 2, 3, 4. Then the children of the first generation, which is the generation 2, will be labeled also from left to right, 5, 6, 7, and so on. If kappa j is the number of children of vertex j, then for a degree sequence S, Ni represents the number of individuals having I children. In this case, N3 equals 1 means there is just one vertex, the root, which has 3 children. And N0 equals 5 means there are 5 individuals which has no children. We denote by PS the law of a tree uniformly chosen from the set of trees with degree sequence S. In this talk, we fix a sequence of growing degree sequences Sn and discuss the convergence of the rescaled profile process, which is the number of individuals in each generation of trees tau n with law Psn. We depict here in this example the profile process, the number of individuals in each generation, which is 1, 3, 3, 2, 1. The main motivation to study this problem is because its relation with real-world networks with given degree sequence and the configuration model. Also, trees with a given degree sequence are more general than conditioned Galton-Watson trees, and we expect this helps to prove the convergence of trees with a given degree sequence to the inhomogeneous continuum random tree, ICRT. Let us define the breadth first walk of a tree T as a path starting at 1 and having increments the number of children of each vertex minus 1. It turns out this is a bijection between trees and excursions, which are paths starting at 1 and being positive up to the first hit time of 0, in this case 10, which coincides with the size of the tree. We add in this picture the profile. Note that the profile and the breadth first walk coincide in certain times. In fact, there is a relation which is depicted in this equation. It says that if Z is the profile of your process, which is the number of individuals at generation J, it can be written as the breadth first walk evaluated at the cumulative profile in the previous generation, where the cumulative profile is just the number of individuals up to generation J. Our work starts in this equation. In fact, if for every n, Sn is a degree sequence, and tau n is a uniform T with that given degree sequence, then the previous equation reads as the profile of your random tree evaluated at time j plus 1 is going to be the breadth first walk evaluated at the cumulative profile in the previous generation. The general idea is to prove that this equation can be rescaled in such a way that the subsequential limits satisfy this equation. If x is the limit of the rescaled breadth first walk, W tau n, then the right-hand derivative of C equals x evaluated at C. Note that this is just the continuous version of this equation. Here we show a simulation of such object. The colors represent the distance of each vertex to the root, the bluest, the farthest. How we construct the limit x? Consider a Catlas path y, starting and ending at 0, and hitting its infimum in a unique time and continuously. The verbal transform by is the path resulting from cutting at the time it hits the minimum and rearranging both paths. You can think of this transformation of changing a bridge to an excursion. We say that a cat-like stochastic process XB has exchangeable increments if we consider this collection of increments XB k over n minus XB k minus 1 over n for every n, and it has the same distribution after permutations. From this definition, we can clearly see that exchangeable increment processes are more general than Levy processes because we are only asking for exchangeability, but not for independence between the increments. Kallenberg gave a characterization of any such exchangeable increment processes. In our case, they are going to be of the form a Brownian bridge plus the sum of positive deterministic jumps compensated and happening at some IID uniform times. And the uniforms and the Brownian bridge are going to be independent. The assumptions of our theorem are the following. Let Sn be a sequence of degree sequences, each with size small sn, and consider their ordered child sequence tilde kappa n. Recall that the child sequence is just a vector with n0 zeros, n1 ones, and so on. The first assumption is that the size of the trees goes to infinity. The second is that there are some positive numbers bn going to infinity, such that they rescale the ordered child sequence. And in this rescaling, they converge to beta j, which are going to be the jumps of your exchangeable increment process. The third hypothesis is analogous to the fact that for a Levy process, the integral of one minimum x squared under the Levy measure is finite. The fourth hypothesis means that your process has infinite variation. So either you have a Brownian bridge part or the sum of the jumps is infinity. And finally, the order of the Bn is going to be smaller than Sn. In the case that there are no jumps, think of this Bn as just the square root of Sn. Our theorem says, rescale the breadth-first walk in this way, the cumulative profile in this way, and the profile in this way. Then first, we have the convergence of the breadth-first walk to this x. The x is described as the verbal transform of an EI process with these parameters, 0, sigma, and beta. Furthermore, if this integral of 1 over x near 1 is finite, then we have the joint convergence of the breadth-first walk, the cumulative profile, and the profile to this triplet, x, c, z, where the c can be described as follows. It is the right continuous inverse of I, where I the t is the integral from 0 to t of 1 over x, and is a solution of this equation. C is the integral of x evaluated at c. Finally, the z is going to be the right-hand derivative of c, and it's also the x evaluated at c. This theorem generalizes the results of Julian and Jor, Dermota Gittenberger, and Kersting. Finally, we give simple conditions for when the inhomogeneous continuum random tree has finite height, which is when this integral is finite, the integral from 0 to 1 of 1 over x. This is also one of our hypotheses. Also, as an application of our theorem, we obtained the joint convergence of the breadth-first walk, the cumulative profile, and the profile of uniform trees with a given degree sequence, having something like a finite variance condition, and also for condition Galton-Watson trees, with offspring distribution in the domain of attraction of an off-stable law. Thank you very much for your attention.